Let's look at how an electric field can be established inside a conductor. If we take a battery with a positive terminal and a negative terminal, and hook it up to a conductor, we saw in the past that surface charge on conductors tends to spread out, like this. And we said that the electric field would be zero at every point inside that conductor. However, that was for electrostatic equilibrium. Current flows in conductors when there's not equilibrium. We are still going to have surface charge, but it won't be static as it appears in this situation. What will happen instead is there will be a gradient of surface charge. Where the number of pluses here represents how much positive surface charge is on that portion of the conductor. And the more pluses you have, the stronger the surface charge. There will be a gradual change from positive to negative. This has the effect of creating an electric field inside the conductor which points from positive to negative. The surface charges will rearrange very quickly, but in any circuit involving a battery and a light bulb, electrons don't have to flow from the battery to the light bulb instantaneously. The surface charges will rearrange very quickly at near light speed, and what this will do is it will cause the electrons that are inside the conductor to just slowly drift opposite the field. It sets up a situation which is like a slow-moving river of electrons. A formula we had used in the past was current equals free electron density times the charge of the charge carriers times the cross-sectional area of a wire times the drift speed. If we divide the cross-sectional area to the other side, it reveals a new formula. The formula is J equals NQ times the drift speed, where J stands for the current density. It's a rate of current divided by cross-sectional area. So for a constant current, the larger the cross-sectional area, the smaller the current density. Take two wires, for example, which have the same current. But they have different cross-sectional areas. Which of the two number 1 or number 2, has the larger current density? Well, if we need to get a certain number of coulombs per second out of this wire, let's say we need to move 4 coulombs per second through this region. Which of them has the higher J, the higher current density? Because of how narrow this piece of wire is, it has the higher current density. And number 2 has the lower current density. Let's try to solve the given problem. If the magnitude of drift velocity of free electrons in copper is 8.49 times 10 to the minus 4 meters per second, what must be the electric field in the conductor? I'm going to start here with the drift velocity. Then I'll calculate the current density. And then from my current density, I'll use this new formula to figure out the electric field. So let's start here with current density. Copper has a free electron density of 8.5 times 10 to the 28. Our charge carriers are electrons. And I plugged in the drift speed, which is a slow speed, 8.49 times 10 to the minus 4 meters per second. I get a current density of 1.15 times 10 to the 7th. The units of current density will be amps per meter squared. Now, in order to relate current density to the strength of the field inside the wire, we can use one of these two formulas. The formula on the left involves what is called conductivity of a material. And conductivity is a measure of how well a material will conduct electricity when a given electric field is present in that material. Some metals will conduct better than others. In the other version of the formula, we see the Greek letter rho, which in this context stands for resistivity. And resistivity tells us how much a given material will resist conducting electricity in the presence of an electric field. They're inverse ideas, and in fact, the conductivity is equal to 1 over the resistivity. Conductivities and resistivities can be looked up on tables using an internet search, for example. So let's look up the resistivity of copper. According to this table, copper's resistivity is 1.7 times 10 to the minus 8. We can compare that to other materials such as gold and aluminum. It looks like gold and aluminum have higher resistivities. So that means that copper is actually a better conductor than them. Now that we know the resistivity of copper, we can go on to solve the problem. I don't have to do this next step, but I will. I'll find the conductivity of copper. It'll be 1 over the resistivity, which is 1 over 1.7 times 10 to the minus 8. The conductivity of copper is 5.88 times 10 to the 7. All right, now let's find the field using either the first formula or we can use this one. Since this second one is solved for field already, I think I'll use that one. We have both the conductivity and the resistivity, so we could use either one. I'll plug in my resistivity for copper. And let's plug in the current density that we had discovered before. The electric field inside this wire must be 0.196 volts per meter. The electric field causes current to flow in a wire that's conducting electricity.